Hi everyone, this is the topic binomial expansions. It's a topic for the International Baccalaureate course, Maths Standard. It's usually taught in Year 11. In this topic we're going to go through binomial expansions. We'll look at Pascal's triangle, then binomial coefficients, and then we'll finish off with the binomial theorem. So let's recall that x plus y all squared can be expanded to be x squared, so the first term squared, plus 2 times x times y, plus the last one squared. So how do we find x plus y all cubed? Well, one way is to take this expression here and then multiply it by another x plus y. So let's do that. And after a bit of algebraic manipulation, doing this term times this and this times this and blah blah blah, we would end up with this expression here, which when we tidied up we'd get this. So let's have a look at x plus y to the power of 4 and x plus y to the power of 5. So just like before, we can multiply the expansion for x plus y cubed by another x plus y. And after we've manipulated everything, we end up with this. And ditto for x plus y to the power of 5. But you can see how it's starting to become quite unwieldy, and we do need an alternate method. So let's have a look at this question. Write the expansion for x plus y to the power of 6. We're going to ignore these coefficients for the moment. Okay, so let's have a look at this pattern here. I start off with an x to the power of 5, so it's obvious where that's come from, plus, and then I've got x to the power of 4, y to the power of 1. And then x cubed y squared, y cubed, x, y to the power of 4, and y to the power of 5. It's just looking at the x's, it goes x to the 5th, x to the 4th, x cubed, x squared, x to the 1, and here I've got x to the power of 0, because remember x to the power of 0 is equal to 1. And for y, we've got nothing, y to the power of 1, y squared, y cubed, y to the power of 4, y to the power of 5. So it's going 0, 1, 2, 3, 4, 5 for the y's. Curious thing here, in every single case for every term, the powers add up to this. Okay, so 3 plus 2 is equal to 5. All right, so let's see if we can write this, and we'll just ignore the coefficients at this point. So it's going to be x to the power of 6 plus x to the 5th y plus x to the 4th y squared, etc., all the way down to here. Now we can have a look at Pascal's triangle, and this is going to help us with the coefficients. You may well have seen Pascal's triangle earlier in junior school, and it goes like this. So I start with 1 and then 1, 1, and then every number in it is the sum of the two above. So 1 plus 1 is 2, and here 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, so all the way down here is 15 plus 6 is 21. So each number comes from the addition of the two numbers above it. So if we want to write the next row, it's going to be 1, then 8, then 28, then 56, 70, and then it repeats. It goes back, so it is symmetrical. And these happen to be the coefficients for those expansions. So remember, one of the ones we had was x plus y all cubed, and it was x cubed plus 3x squared y plus 3xy squared plus y cubed. So now, remember the one we did, which I think was x plus y to the power of 6? There are the coefficients there. So this one here, x plus y all squared, has got 1x squared plus 2xy plus 1y squared. Here's x plus y to the 4th, 1x to the 4th, 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4th. And here's another one. Here's this x plus y to the power of 6. So we had all of these pronumerals, but we didn't have the coefficients, and there they are. So if we want to write the expansion for x plus y to the power of 8, remember we're going to go x to the 8, and then x to the 7, x to the 6, all the way down to 0. And y will start with y to the 0, then y1, y squared, y cubed, etc. And here are our coefficients. So x plus y to the power of 8 will be x to the 8 plus 8x to the power of 7y plus 28 x to the power of 6 y squared plus 56 x to the power of 5 y cubed plus 70 x to the power of 4 y to the power of 4 plus 56 x cubed y to the power of 5 plus 28 x squared y to the power of 6 plus 8 x y to the power of 7 plus y to the power of 8. So pretty long expansion to do, but much easier than doing it the long way that I showed you before. Quick check, just make sure all the powers add up to 8 in each case, because it is easy to get confused when you're doing this. So let's have a look at some other expansions. So here we've got x minus y all squared, and we don't actually need Pascal's triangle for this. We can just do the expansion that we learnt in years 9 and 10. First one squared, so x squared minus 2 times x times y plus y squared. Okay, how about this one? Let's use this third line here, Pascal's triangle. So it's going to be a cubed plus 3a squared multiplied by negative b plus 3a multiplied by negative b all squared plus negative b all cubed. All right, let's have a look at all of that. Tidying that up, I get this. Now what can you notice here about the pluses and minuses? It's also similar to this one. Can you see how they oscillate? So if you're asked to do an expansion like this using Pascal's triangle, and you've got to do the whole expansion, you can actually just oscillate these pluses and minuses. So it starts off positive, then negative, then positive, then negative. Later on, when we're asked for a particular term, you'll have to do it this way, but I'll go through that again then. So if we're doing the full expansion, this is unnecessary here. Can you see why it's oscillating? This is a negative b to the power of 1, so that minus will stay. Here, I'm squaring out the negative. So minus b times minus b is positive b. Okay, so that's why it oscillates. Odd power, even power, odd power. Let's try this one. So I'm going to get this time 2x all to the power of 4 minus 4 times 2x to the power of 3, and I don't need to worry about the 1. 1 to the power of anything is 1, plus 6, and then 2x all to the power of whatever I was up to, 3 I think. Let's have a look. It's easier to write down. So 2x to the power of 4 minus 4 times 2x to the power of 3 plus 6 times 2x squared minus 4 times 2x to the power of 1 plus 2x to the power of 0. You can't stop here, you've got to tidy that up. But you can just do that on your calculator. See again how it oscillates. And then finally have a look at this one. And we're starting to get into the questions that you actually will get in the paper. So here I'm going to have x cubed minus 3 times x squared, and then this, plus 3 times, let's write it down, x cubed minus 3x squared times that, plus 3 times x, and then this all squared, and then finally minus 1 on x cubed. And when I tidy that all up, the powers actually end up being a little bit different to these ones here. So x squared divided by x is x, x divided by x squared is x on the denominator. Now the numbers in Pascal's triangle are denoted by NCR, or we can write it in this bracket form. It still means the same thing though. N is the row number and R is the position in the row. But here's the trick. The first number, this 1, is the 0th term in the 0th row, which is a little bit annoying. So this is the 0th row, the first row, the second row, the third row, the fourth row. So basically it's this number here. It tells you which row it is. This is also, this first element is the 0th term. So this is the fourth row, and the 0th term, the first term, the second term, the third term, the fourth term. So that can be really confusing. So let's find the following. 7C3. So we come down here to where n is equal to 7, and we want r is 3. Okay, so remember we're starting with 0. 0, 1, 2, 3. 7C3 is 35. What about this one? 5C4. So we come here to here. I know this is the 6th row, but this is where n is equal to 5. we want r equals 4. So 0, 1, 2, 3, 4. So 5C4 is 5. So on the calculator, what we've got to do is go into run and then hit the number 10. So that's going to give us this 10 here. Actually, it's going to look like this, 10. You go into option, so that's quite important there. And then F6 to get the next menu. So that's this part here. And then you hit F3 for probability. Now, once you get that, you're going to get this screen here. And you can see NCR sitting there. So you hit F3. And it will end up going 10C. And then you just type the number 5 and press equals. It is quite difficult on the graphics display calculator. If you want to take your normal Casio calculator, your scientific one in, it's much easier. It's sitting there above the divide sign. So you'd go 10 shift divide 5 equals. You are allowed to take 2 calculators in if you want to. Let's go through this again. It is confusing. So you're going to run. That's fairly intuitive where it would be. You've got to put this first number in first. You can't do the NCR first. Otherwise, it'll give you an error. So you've got to do this N part. So hit 10, then go option. That's the big thing here. F6 to get the arrow to go to the next screen. Then go into probability. I will chat a little bit about why this is probability later on. And then you will see this here with NCR. Then hit that and it's okay from then on. Then the 5 equals. And we get 252. Now there is a formula for NCR, and this is it here. So NCR is equal to n factorial, that's what that means, divided by r factorial times n minus r factorial. Sometimes these are written the other way around. It's okay, it's multiplication, so it doesn't matter. Now n factorial means n multiplied by n minus 1 multiplied by n minus 2 all the way down to 2 times 1. So for example, 7 factorial is 7 by 6 by 5 by 4 by 3 by 2 by 1 gives you 5040. Now on the calculator, the factorial button is in the same menu as NCR, so that's convenient. Here it is here. So if we want 6 factorial, we type the 6, navigate our way through to this menu, and then hit F1 and then equals, and it'll give us 720. You can take the scientific calculator into the exam if you want to. Then it's got a dedicated button. It's sitting above the reciprocal button. So you would do 6, shift, then hit this button, then equals. Before we finish with factorials, I need to tell you that for convenience, naught factorial is equal to 1. It has no reason to be equal to 1 other than for convenience. So it's so that the formulas work. So if you do that, you can check it out if you like. 0 factorial, it'll come up with 1. All right, so let's calculate 7C4 by using the formula. Okay, so 7C4 will be 7 factorial over 4 factorial multiplied by 3 factorial. These two will always add up to that. Now we're going to expand it out. Now you can see here how this bit here can cancel with that part there. So that leaves me 7 by 6 by 5 divided by 3 by 2 by 1. And 3 2's are 6. So they can cancel out as well. And so our answer is 35. I think that could be asked in the non-calculator paper. So you do need to know how to use that and how to cancel these sorts of things out. They wouldn't give you a horrendously difficult one though if they did do that. Now there are a few relationships within Pascal's triangle. You've probably seen the symmetry and the ones lying all the way down. There's a couple of other curious things. Here are the counting numbers and here are the triangular numbers. Do you remember them? They're the ones that look like the 10-pin bowling numbers, like the 10. So they can be made into triangles. That's not all that important. The important parts are NC0 is equal to 1. So all the way along here, they're always equal to 1. NC1 is always equal to n. So these are these here. So when n is 4, 4C1 is equal to 4. And the symmetry. So if you take any entry, say this one here, this is NCR, it will equal NCn minus R. Okay, so there's 21s here, 56s here. So let's give an example of each of these. So this one here, well, let's choose 7C0, that will equal 1. 6C1 will equal 6. Let's have a look at this one here. 4C1 will equal 4C3. Okay? So the binomial theorem states that a plus b to the power of n is equal to nc0, a to the n, b to the 0, plus nc1, a to the n minus 1, b to the 1, plus dot, 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 plus, here's our general term, nc n minus r, a to the n minus r, b to the r, plus dot, 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 here's the last term, ncn, a to the 0, b to the n. It's more commonly written like this, so it's just abbreviated a little bit. Let's have a look how we've got from here to here. nc0, we just learnt that that's equal to 1. b to the 0 is equal to 1, so I can write that as a to the power of n. Then that term's the same, this term's the same, and here, instead of ncn and a0, I've just written the b to the power of n, because that's equal to 1, and so is that. So let's use the binomial theorem to expand 2a plus 3 to the power of 5. So I'm going to use this formula here, because I'm going to do the first term to the power of 5, plus 5c1, first term to the power of 4, last term to the power of 1, plus, let's have a look at it so I don't get confused. So 2a to the power of 5 plus 5, 2a all to the power of 4 times 3. Then I've got 5c2, 2a all cubed, 3 squared, plus 5c3, 2a all squared, 3 cubed, plus 5 times 2a times 3 to the power of 4 plus 3 to the power of 5. So have a little bit of a practice expanding these out. Let's tidy it up. So I end up with 32a to the power of 5, 240a to the power of 4, plus 720a cubed, plus 1080a squared, plus 810a, plus 243. Now on the formula sheet, we get the binomial coefficient, which is NCR is equal to n factorial over r factorial multiplied by n minus r factorial. And we also get the binomial theorem, which is the expansion of a plus b to the n. So it's written out for you in full, and it includes the general term here in the centre. So let's see how we might use that general term. Here's a question. Write an expression for the term in x to the power of 10 of the expansion 1 plus 6x all to the power of 15. So all we want to do here is match this a plus b to the n to what we want. So we can see that this is going to be a, 6x is going to be b, and this 15 is going to be n. All that we have to do is figure out what r is. So let's have a look here. I want that n, there's going to be 15, a is going to be 1. It's this bit here that's going to tell us what r is, because if we put 6x in there to the power of r, we're going to want r to be 10. Okay, so n is 15, r is 10. All we do is substitute it in. 15c10, 1 to the power of 5, 6x all to the power of 10. And we can leave it like that because it says just write an expression. We can also use the formula to find the coefficient of a particular term. So suppose we want to find the coefficient of the term in x to the 8 of 1 minus 2x all to the power of 12. So again, like we just did, this is going to be a, minus 2x is b, and this is n. So n is equal to 12. When I substitute that into the formula, we want this raised to the power of 8, so r is 8. Substituting it in, we get 12c8, and then a is 1 to the power of 12 take away 8, which is 4. And then see how I've included the negative in here. So this is negative 2x all to the power of 8. And tidying that up, I get 126,720 x to the 8. And so the coefficient is 126,720. Let's try a harder one. For the expansion 2x squared take 3 on x all to the power of 15, find the term in x to the power of 21. I'm going to start the same way with our general term, and we know that n is 15. We know a is 2x squared, and we know b is negative 3 on x. I've turned that around into index form. but we don't know what r is, so we're just going to leave that as it is. I find one of the easiest methods with this is to split it into individual bits. So you can see I've done 2 to the power of 15 take r, and then x to the power of 30 take 2r, multiplied by minus 3 to the power of r, and then x to the negative r. And now we want to grab these x bits together. So when I multiply pronumerals that are the same, I add the indices. So I've got 30 take 2r plus negative r. So there it is there. And so we know that 30 take 3r is going to equal 21. So it's just a simple equation, making 3r the subject, and then dividing by 3 we get r is equal to 3. And so now all we have to do is substitute in for r and tidy it up. So the term is going to be 15c3, 2x squared to the power of 12, negative 3x to the negative 1, all to the power of 3. And if we do a bit of arithmetic and algebra on that, we're going to get minus, let me see, what number is this? 50,319,360 x to the power of 21. Here's another one. Find the constant term in the expansion x squared plus 1 on x all to the power of 6. So constant term means there's not going to be any x's, or in other words, we're going to have x to the power of 0. So we're going to follow the same method. Here's our general term. So we've got 6cr, and here's a, which is x squared, to the power of 6 take away r, and here's b. I've changed it around to be x to the negative 1, and that's to the power of r. Okay, tidying it up a little bit, I get x to the power of 12 take 2r, and then x to the negative r. And so we want that to equal x to the naught. So we want 12 take 2r, take away r, to be equal to 0. So that's 12 is equal to 3r, and so r is equal to 4. Now all we have to do is substitute that back into here. So we get 6c4, x squared all to the power of 2, x to the negative 1 to the power of 4. Tidying that up, we get 15x to the power of 4 multiplied by x to the power of negative 4. And you can see that this is going to cancel out. And so our constant term is 15. Now just a couple of things to remember. R is related to the position of the term in the series. And so as such, it can't be a decimal and it can't be negative. And also can't be bigger than n. So here's an exam question. In the expansion of ax cubed and then in brackets 2 plus ax all to the power of 11, the coefficient of the term in x to the fifth is 11,880. Find the value of a. So given we're multiplying by this ax cubed, we actually only want the term with an x squared in here. And we could go through and do the general term, but I know it's going to be the third term. The first term's got no x's, the second term will have one of these, and the third term will have this one squared. So I'm just going to expand it out a bit. So here's my question, then ax cubed, there's the first term, here's the second term, here's the third term, 11c2 times 2 to the power of 9 times ax all squared. Alright, let's grab this bit times that and put it equal to 11,880 x to the power of 5. Alright, I've got an x to the power of 5 here. I'm going to drop those from both sides and tidy it up. And now we need to solve for a. So divide both sides by 28,160 and then do the cube root and we get a is equal to 3/4.